left off last time talking about a couple of different relationships between the solubility of solids in liquids like salt or sugar in water, or here are some examples of different compounds and their solubility in water.
You are now unmuted.
Okay, so last class we started talking about, or last class we ended sharing some ideas related to the solubility of solids in something like water, in a solvent like water, right? We know that solids dissolve in water to a degree, and we know that if you heat up the liquid that you're trying to dissolve the solids in, what do you think, Robert, when we heat up liquids? Robert, are you there? Camille, are you there?
Yeah, I'm here.
Okay. What happens to the solubility of a solid when we dissolve it in warmer liquids? Does it increase the solubility or decrease the solubility of the solid?
Increase?
Increases the solubility. That's right. All right. And then we also had a conversation about gases. Do you remember that one, Camille? How did warming up solutions change the solubility of gases in water or liquids?
Does it decrease?
It decreases. That's right. And the two models that I like to offer people so that they can think about their own lives. If you take a soda and you let it get warm, if the soda gets warm, then it will expel the carbon dioxide easier. So that carbon dioxide no longer becomes soluble in the liquid. The other model is a bowl of cold cereal milk, right? You put some sugar in that, and it won't dissolve very much of the sugar because it's very cold, and so the sugar makes a pile at the bottom. It doesn't mean it doesn't dissolve any of it. It just won't dissolve as much. All right. Now, we have this slide here, and I'm going to make this slide. Let's try that again. There we go. I'm going to make this slide mini screen here, and then I'm going to kind of just hide it a little bit, and we're going to try to learn something about these numbers here. 8.42 times 10 minus 7, 1.66 times 10 minus 4, 4.48 times 10 minus 5. Knowing nothing at all, only knowing what units are provided here. Okay, Sarah? Could you help me with this? And this is kind of, mimicking where you might find yourself in an exam. So you find yourself in an exam, you're like, oh man, we talked about this a long time ago. I can't remember what this means. Well, like I've said before, the units can often indicate what kind of number this is, what it's signifying or helping us understand, or what it's supposed to be useful for. All right, Sarah, what are these units here? What are these units? Can you tell me what those are at all? What's big
the
M?
M is molarity.
Molarity, good.
And then that is millimeters of mercury.
Uh-huh. What kind of unit is molarity, first of all?
That is concentration.
Concentration, very good. And what is millimeters of mercury?
That is pressure.
Pressure, very good. So what do you think is going on here where it says molarity per millimeters of mercury, or torr? Torr is another unit that's the same as millimeters of mercury. Molarity per torr. What would that mean?
I am not sure. So is it concentration? Yeah, I'm not sure.
Well, molarity, so we're talking about the concentration of something dissolved in a liquid, right? Per torr. So
Yeah.
could that mean something like this? If I have some sort of a container here, and this container is full of some liquid, and apparently the concentration, the molarity of whatever in here depends on what? What does it say it depends on?
The pressure.
Yeah, the pressure. The pressure. So hopefully, when we think about that, how in the world is the molarity going to depend on the pressure? Well, what they're saying here is the pressure of the gas above that liquid will depend on the molarity that actually dissolves in the liquid. So, for example, 8.42 times 10 to the minus 7 molarity for every millimeter of torr, or millimeter of mercury, or torr, that you have of that gas above that liquid. Did you follow that, Sarah?
Yeah.
Okay, so if we look at this slide more clearly now, we see that we have this constant, which they tell us is called Henry's constant. And we don't need to remember that name necessarily. Constant, K, usually stands for constants, and there's lots of them out there. But we have different values, and it depends on the gas, right? So certain gases are more soluble in water than other gases, right? But as long as we know this, we can identify how much of the gas will dissolve for every given pressure. All right? So here's an example of a problem, Alyssa, if you could help me out with this one. What's the concentration of dissolved nitrogen in a solution that is saturated in nitrogen at 2 atmospheres? 2 atmospheres.
Would we have to convert the atmospheres to millimeters?
Yeah, good. Millimeters of mercury. Do you happen to remember that by chance?
I know it's a constant, but no, sir, sorry.
And that's not a big deal. They would give us that sort of thing, right? I think it's 760 millimeters of mercury is equal to
I think that's right.
1 atmosphere. Okay, let's just use that. It'll get us close enough. So then what else are we going to do with that? How are we going to proceed here?
If it's asking for the concentration, we'd want to make a conversion so the molarities on top. So we could use the constant of molarities over that and then have the converted atmosphere so that the millimeters and
Okay, so we want molarity on top here, right? And we know that they've given us what the molarity will be for a given millimeters of mercury. I think that's what you're saying. Set this up like that, right?
Yes.
And then what would go here?
Well,
looks like it's going to have to be millimeters of mercury, right?
Yes.
To get rid of that.
And the converted 2 atmospheres is 1,520.
All right. So 760 millimeters for every 1 atmosphere, and they say that we had 2 atmospheres. Is that what the problem says?
Yes, sir.
All right. There we go. So from this business here, we should be. Oh, what number do we have to put in here?
The 8.42 times 10 to the negative 7.
All right, 8.42 times 10 to the minus 7 molar is what we get for every millimeter of mercury. All right, good. So I think, again, the idea here is we use the units that are given to us to kind of help us understand the kind of finagling we have to do with our numbers to get the right answer, right? Okay. Here we go. Robert. When you open a bottle of seltzer, it fizzes. How should you store it to increase the time before it goes flat? So if you don't want it to go flat, if you don't want the carbon dioxide to come out of solution, what are the things that we would like to do?
So you are going to want to cool it and pressurize it.
All right. So we want to cool it and pressurize it. So which one is that? Oh, B. Okay.
B.
Cool it and pressurize it. Very good. We know that the higher the pressure you have here, the more will dissolve, and then cooling it also increases the pressure. I don't know if you guys have ever had a tank of carbon dioxide in your kitchen, but sometimes we do that. You can just buy tanks of carbon dioxide, and then you can fill a bottle up with water, put the lid on top, open up the tank, and then you just shake the water to increase the surface area, and then you can wait, cool down the water. That helps as well. And when you're done, you take off the tank, put on a lid, and you get carbonated water. And then you just add some sugar and flavoring, and then you can get yourself a soda pop, right? All right. Just like the amount of gas that will dissolve in a solution depends on molarity, right?
I have a question.
Yeah, go ahead.
What does the M stand for right there? Is that just molarity?
Big M?
Yes.
Yes, that's right. That's moles of solute per liter of solution.
Okay, thank you.
Yeah.